Tamam, başlayabiliriz.
Hello, everyone. One of the speakers of today is Antigona Pajaziti. She is a graduate student at Sabancı University. She's going to talk about linear codes today. If you have any question, you may use chat box. Now it's your turn, Antigona. Hey.
Thank you, Gülsen. Merhaba herkese. So I will share my screen. Herkes görebiliyor mu?
Evet. Bence görebiliyorum.
Okay, so today I'm going to talk about linear codes, and I catch the last part of the talk of Fatma Hoca, and she mentioned coding theory. So this will be a good follow-up if somebody is looking at my talk also. So the birth of coding theory was inspired by a classic paper of Shannon in 1948. And from that moment on, a great deal of research has been devoted to finding efficient schemes by which digital information can be coded for transmission through a noisy channel. And also, coding theory, as previous professor talked about, is an application of pure mathematics like linear algebra and field theory. So today I'm just going to give that part of the coding theory for linear codes. So the main idea is that we have the message. So we have the message source here. We take the message from this box and we send it to the encoder. Encoder encodes it as a code word, and then it sends it to the channel. Now, the channel can be a telephone, it can be a radio link, or it can be a satellite communication. So sometimes it can be noisy. And after the code word passes through the channel, we get our received vector, which is not always the same as the code words. For this reason, this received vector is sent to the decoder, which decodes it, and then sends it to the user. Now, our aim is always for the difference between the received vector and the code word to be as minimal as possible for us to understand the message which is sent by the message source. As an example, a simple example, I wrote this one. So suppose that we have yes or no as message source, and we want to send it to some user. Now, we want to send the word yes. Now, yes passes through the encoder. So the encoder encodes yes as 5 zeros and no as 5 ones. So it's from yes, it sends it as a code word to the channel. Now suppose that the channel is noisy, then the received vector is 01001. So we see here that two of the digits are different. So we have two errors. And when the decoder gets this received vector, then it decodes it at the nearest code word, which in our case, it is Y, it is yes. And then it sends it to the user as the message yes. So here we're going to, just a second. I'm going to show you the structure of the code so we can understand it better. Why do we want the error to be minimal? So this is the structure of the code. It's represented as a matrix, so n by n matrix. So n is the length of the code word, and m is the number of the code words, which go down as I wrote 3 dots. And these digits or these entries in the code word, they belong to a certain family. And all of this is called a block code. Now, a good code C, we name it by C, has small n, so the length of the code word is small for fast transmission, has large m, so a large number of code words to enable transmission of a wide variety of messages, and has large d to correct many errors. Now, what is d? By d, we denote the Hamming distance between two code words. What does this mean? It means that the distance between two code words, it means the number of places in which they differ. Now, what do I mean for large D to correct many errors? We will see it after this slide. When we are checking the distance between the two code words, we will always have a minimum distance. We denote the minimum distance by d of c, and we see that this Hamming distance it satisfies three conditions. So the first one, the distance between two code words, it is 0 if and only if those code words are equal to each other. The second one, the Hamming distance has the symmetric properties, so it means that the distance between x and y, it is equal to the distance between y and x, where both of these x and y are code words, and it satisfies the triangle inequality. If we know the minimum distance, we can tell for this code to how many errors it detects and how many errors it corrects. So this theorem tells us that a code C can detect up to S errors in any code word if the minimum distance it is greater or equal than S plus 1, and a code C can correct up to T errors in any code word if the minimum distance it is greater or equal than 2T plus 1. So I'm going to write the proof of the second one, and then the other one is also kind of the same idea. Okay, so let this, if this minimum distance, it is greater than 2t plus 1, and let this be the code word, the center, so that its neighborhood up to t errors, I can show it as a circle. And let this be another code word, x prime. So again, then its neighborhood t, I can just show it like this as a circle, or actually they use spheres. Now these two, if this holds, these two neighborhoods of two different code words cannot overlap. So what happens if they overlap? If they overlap, they will have a place of intersection. So this is the center x and this is the center x prime. And suppose that the received vector, it is y here. Now, when we check the distance between these two code words, then we can use the triangle inequality, so the third condition, and we can say that this is less than or equal distance between x and y plus distance between y and x prime. And the radius here was t, and here as well was t. So I know that this part is less than t, and this part is less than equal than t. So this would be less than or equal to 2t, and this contradicts our minimum distance, what we assumed before. So a code C can correct up to t errors in any code word if this minimum distance it is greater or equal than 2t plus 1. Why is this important? Because if we have that the minimum distance, let's say, of a code it is 3, then we can tell up to how many errors can detect or correct. For example, we can write t as 2 plus 1. And now I can tell that this is our S, and I can say that this code with this minimum distance can detect up to S errors. And I can write this 2 times 1 plus 1, and I know that it can correct one of those errors. So this is why it's important. Okay, so finally, this is the main thing that I'm going to focus on. So it's the linear codes. Linear codes are defined over finite fields, and finite field is a field with finite elements, and its order is a prime power. We regard to this fq to the n as the vector space, and we denote it by v and q, where n is the length of the code word and q is the order of the finite field. So a linear code C over this finite field is a subspace of the vector space v of n and q for some positive integer n. What does this mean? It means that if you give me any two code words in our linear code, then their linear combination is also in the linear code. So that's what the subspace of a vector space means. This will be really helpful for us. We will to specify a linear code. Now we denote this linear code by this notation, so bracket nk, where n is the length of the code word and k is the dimension of C. What do I mean by dimension of C? we recall from linear algebra that a basis for a vector space V is a set of linearly independent vectors which span V. And then the dimension of that vector space V is the number of the vectors in the basis. The same idea here, the vectors are the code words. So those linear independent code words, which also generate our code word and the vector space, is the basis for that vector space. And the number of the code words in that set is the dimension of C. So in linear code, we also define weights, which we noted by W of X. And this weight, W of X of vector X, is defined to be the number of non-zero entries of X. For example, if we have 0, 1, 0 to be X, then this weight of X is going to be 1 because it has just one entry different from 0. Now, I wrote here some facts that I'm not going to prove, but you can find their proofs easily in every book that explains coding theory. So if we have two vectors in our vector space, then the distance between X and Y, it is equal to the weight of X. And also, the second fact that if we denote by W of C the smallest weight of a code word in the code, then, and also of non-zero code words of C, then the minimal distance of the code, it is equal to the minimal, to the smallest weight of the code. Why is this important? This gives us a really good advantage for linear code. So the first one, I wrote it here, that for a general code with app code words, now to find the minimum distance, we have to make M choose two comparisons because we just compare each two code words, and then that is how we find the minimum distance. But by this one here, that for a linear code, the minimal distance is the minimal weight, then we can just check all of the entries one by one. We don't need to compare two, and that will take us only M-1 steps. So this is one of the advantages. And the second one is that to specify a non-linear code, we may have to list all of the code words, but to specify a linear code, we can do it by just giving the basis of the K code words. As I said before, these are linearly independent and they span our vector space, so they can generate our code. So that was called a basis, but here for this code, I can just call it a generator matrix because it's generating the code. So I gave the definition here, since we're looking at the codes as matrices. So a K by N matrix whose row form a basis of a linear NK code is called a generator matrix of the code. Now, what do I mean by this? If this is our linear code, so as you can see, this is 3 by 2 because the length of the code word is 3 and 2 is the dimension. Why? Because I can just check these code words one by one and I can see that the generating matrix will be 0, 1, 1 and 1, 0, 1 because these are the two code words that are linearly independent. Why it's not the third one? Because when you add the second and the fourth one, because when you add the second and the third, it will give you the fourth code word. And of course, and if you add all of this second, third, and fourth, it will give you the first code word. So the generated matrix would be a 2 by 3 matrix. And again, if I'm not given the code word, if I'm just given the generator matrix, I can again write the code because I know that these two code words are in the code and any linear combination of those code words is also in the code. Some other facts, we have that the linear code C contains Q to the K code words. So Q was the order of the finite field and K was the dimension of the code. So given the generator matrix, I can also say immediately how many code words our linear code has. So if we get more than what Q to the K is, then we know that there is a mistake. And of course, and another fact, we have that all linear codes, they contain the 0 vectors. So if only this would given, I would first write 0, 0. I would write 0, 1 and 0, 1, and then I would add them up, and this will be 1, 0, 0. And because this is 2, and I am working over a finite field with 2 elements with 0 and 1, then I would know that there are 2 to 2, so 4 code words. So I will know that this is the code that I'm looking for. So this is one advantage. Now, if you remember the first scheme that I showed you, so we have the message, and the message is sent to the encoder. So how do we encode those messages? So if we have this, let C be a linear code over a finite field with Q elements and with the generator matrix G, and let this U be a message vector. So we encode the message vectors. So this is of length n. Okay, so sorry, what this is n. By multiplying it in the right by the generator matrix G. So what we take U and we send it to U times G, and this is the result that we have. So this is a linear combination of the rows of G. Now, what we said before, the rows of generator matrix G, they are all code words. And because the linear code is a subspace of our vector space, then the linear combination is also a code word. So it means that this encoding that we're doing, U times G, will be a code word, because that is what we need. Now, for an easier way to do this encoding, we can write our generator matrix in a standard form. So this is called the standard form of G. So here we have the identity matrix. And in the right part, we have A, which is the K by N minus K matrix. Why is this easier? Because now, when we multiply U by G, the first K digits will be the message digits, and from the xk plus 1 to the xn will be the check digits. Now, these check digits represent redundancy, which has been added to the message to give protection against the noise. So, for example, let this be a binary 7 by 4 code. Okay. Let this be a binary 7 by 4 code with a generator matrix G. So I know that the dimension is 4, and I am working with binaries, so it will have 2 to the 4 code words, and the length, this is N, and this is K, is 7. But here I don't have to write all the code, so because I have the generator matrix, and if this will be a message vector, then when I multiply this message vector with our G, I will get this vector here. So, for example, if the message gives me, if I will have this 0, 0, 0, then by this method, it would be encoded as, so this is U1, U2, U3, U4. I will just write them, substitute them here, and I will get all the 0 vectors. And the same idea goes with 1, 0, 0, 0, and this will be encoded by just writing U1 is equal to 1, and the other U's are equal to 0. I will be having this one, and the same idea with the third one. So until now, what we saw is that if we have the message vectors, and it to the encoder, and the encoder gives us the code word. Now we are going to send this code word through the channel, which might be noisy. So we are going to check the methods of how can we decode the received vectors.
Antigona, I didn't understand how we create message vector here.
Here, no, you just give it. It depends like how you're going to give the message vectors. And then when you send it to the encoder, if you remember, wait, let me go here. You send it to the encoder, and then the encoder decides on what digit is going to represent it, and then it sends it to the channel.
In the example, can you go back?
where was I? Okay.
In the example, we have a message vector, right?
Yes, but I mean, I don't know how to explain this because the computer does it. So you
okay.
just give it to the computer, and then you decide on the alphabet of the code, the finite field, and then it just goes on.
Okay, thank you.
Okay. So, okay, where was I? So this is the code word and the channels. So now we are going to look at the decoding with a linear code. So we send the code word through the channel, and let's name it with this. This is the code word, so x, x1, x2 to xn, and this is sent through the channel. And the received vector, let's name it by y. So as I said, if the channel is noisy, then the received vector might not be the same as this code word. So the error we represent it by e, which is the difference between the received vector and the code word. And we always want this to be minimal, because if it's too big, then we will not understand what was the message that was sent. I'm going to give a definition here before I explain you one of the methods of decoding. So suppose that C is an NK code over this finite field, and that A is any vector in this vector space. Then this set, so A plus C, the set of all A plus X, where X is a code word, this is called a coset. So this is a definition of the coset. And if actually, yeah, like I didn't recall group theory, since this is also given a definition here, but people who maybe took group theory or algebra 1 might know what a coset is. So this is the definition of a coset. Now the theorem, suppose that this C is an NK code over this finite field. Now what do we know? We know that every vector in this vector space is in some coset of C. What do I mean by that? If I have this A vector in our vector space here, so I can write A as A plus 0. And I know that the 0 vector, it is in the linear code, as I said before. So I know that this will be in this coset. So every vector, I can represent it like this, and it is in some coset of C. Now, every coset contains exactly q to the k vectors. I gave it before that every code word contains, so the order of the code is q to the k. Now there is one-to-one correspondence between A and the between the elements in the code word and the elements in the cosets. So this gives us that the order of C, it is going to be equal to the order of the coset, and we already know the order of C. So the order of the coset, it is equal to q to the k. And the third one, it says that two cosets either are disjoint or they coincide. So let's suppose that they let's suppose that they intersect at some point. So if we have a code word in our vector space, let this be an element of so B plus C and a coset, an intersection with D plus C. So this would mean that A can be written as B plus X for some code word in C. And A can be written as D plus some Y from some Y in C. And this means that A, it is equal to B plus X equal to D plus Y. And from here, actually, yeah, we can, how can we say? So yeah, we can see that B, it is in D plus Y, and D, it is also in B plus X. So they are, so D is in B plus X and B plus X in D plus Y, so they are equal to each other. So they cannot intersect, they either coincide or they disjoint. Okay, so why did I give you the cosets? Now we're going to see look them over the code words. So the vector having minimum weight is called a coset leader. So the minimum weight was the number of non-zero entries in a code word. Now let this C be a binary 4x2 code with the generator matrix of this form. So 1 0 1 1 and 0 1 0 1. Now I know that it's okay, it is equal to 2. And binary, we are working with 2 elements. So 2 to 2, it is equal to 4. So I know that there are 4 cosets. And also the code, the linear code contains 4 code words. And I know that 0 0 0 vector belongs to the code word. I know that the code word in the generator matrix belong to the code word and their linear combination, which gives us the 4th code word. Now, what I do, so the first coset will be C itself. The second coset, I look at the code words in the set in the C. So I'm going to pick one vector which has minimum weight, and it is not in the C. So one vector of minimum weight that I know is 1 0 0 0 plus C. So this is what like our A. And I just add them up with a vector in C, and I have the second coset. The same idea. Again, I pick a vector with minimal weight, and then which is not in the first coset, and it's not in C. Then I add it to the vector, and I get the third coset. And then again, the same idea, I get the 4th coset. Why do I stop? Because I know that there are 4 cosets. If I continue, I will get again one of these cosets. So now I have the cosets. What I'm going to do, I'm going to write them in a standard array. So for here we have the first, so these were our A's. And then here are the other entries of the cosets. So we looked at it like this. So the coset leaders, these are the code words, and the coset leaders are in the first row because they are of minimum weight. Now, what do I do here? We note that each entry is the sum of the code word at the top of its column and the coset leader at the extreme left on its row. Now, by choosing a minimum weight vector in each coset leader, we ensure that standard array decoding is the nearest neighborhood decoding scheme. Now, when Y is received, its position in the array is found, and then the decoder decides that the error vector E is the coset leader found at the extreme left of Y, and Y is decoded as the code word, so Y minus the error at the top of the column containing Y. What did I say with this? So let's say that we received this vector. What do? I look in the array and I found it, and I see that it is here. So by this decoding scheme, I know that the error, it is the coset leader on its left. And I have this is Y and this is E. So Y minus E will give me X. And by the decoding algorithm here, I know that X must be in this column. And then I found that 1 1 1 minus 0 1 0 0, it will give me 1 0 1 1. So this is our code word. This is one of the ideas of decoding received vector. But of course, this is real. It's slow when we deal with large codes. So it is just good when we're dealing with not with small length codes. Did I say it right? Yeah, small length code. So that's why, and also if we're dealing with large codes, because it is slow and it costs 2 storage requirements, so it's not required when you're working with large codes. That's why I'm going to present you another decoding scheme, or let's say, yeah, or algorithm, let's say it like that. But first, to do that, we have to know what dual code is. So a dual code, it is the set of all vectors such that their product with the code words is equal to 0 for every code word in C, and we denote it by this notation. Now, what this dual code, now we know that the C linear code is N by K code, and the dual code is also a linear code. it is with the length n and the dimension n minus k. Why dual code is also good? Because I know that if I know the generator matrix, then and I want to find the vectors in the dual code, then I can just use this theorem here. So this vector is in the dual code if and only if its product with the transpose of the generator matrix is equal to 0. Now, why is that? Because, okay, so I know that the generator matrix rows are code words. When we look at its transpose, there will be columns. So it will be V times some, let's say, Ri column of G, and by definition, if this is equal to 0, then V is in the dual code, as we see it in this set, and from the other side as well. So because this dual code is a linear code, we said before that linear codes have generating matrix, and this dual code has also a generator matrix, which we noted by age, and we call it a parity check matrix. This matrix is a n minus k by n matrix. Now, why do we need all of this? Because we saw before that we can specify a linear code by just knowing its generator matrix. But now I can specify a linear code by just knowing the parity check matrix as well. So I don't need just a generator matrix. So we're finding more ways that we can specify a linear code. What does this mean? Now I can say that this code contains all x that are in this vector space, such that x times the transpose of parity check matrix, it is equal to 0. So, and of course, because this is a generator matrix, and earlier I said that for G there is a standard form. There is a standard form for a parity check matrix as well, and we can just write it as B on the left side, and the identity part matrix will be on the right side. This is actually good. Okay, I didn't add it here, but there is this theorem that says that if we know the parity check matrix, we can also, in the standard form, we can also find the generating matrix, and it's an if and only if statement. So earlier, the decoding scheme, we just needed the generator matrix and the cosets. Here, I'm going to present something called syndrome decoding. So if suppose that age is a parity check matrix of a linear code C, then for any vector in our vector space, this S of y equal to y times H transpose, it is called the syndrome of y. And this is a vector, so it is 1 by n minus k row vector. Now we know that there is a one-to-one correspondence between the cosets and the syndromes. If the rows of H are denoted as H1, H2, H3 to Hn minus k, then the syndrome of y will be, the entries will be y times those rows. And also the third one, we have that if S of y is equal to 0, then y is in C and the other way around. So why is this? Because if S of y is equal to 0, then H transpose is equal to 0. And by previous definition here, then X is a code word in C. Y is a code word in C. Okay, so let's see this all in an example. Let us have a binary, so linear code whose generator matrix is this one, and the parity check matrix, it is this one. And actually, this is the same code that I used before. So what do we do first with the syndrome decoding? We first find the syndrome of the coset leaders. So how do we do that? So the first coset leader was 0, 0. So I take 0, 0, and I multiply it with the parity check matrix, its transpose. I have 0, 0. Then 1, 0, 0, 0. I do the same thing, and I have 1, 1. Then 0, 1, 0, 0. When I multiply it by the transpose of parity check matrix, I get 0, 1. And the last one, it is 1, 0. So I add now one column more to the standard array that we saw before. So we have the coset leaders, we have the code words, and we have the syndromes. Well, why this method is faster? Because now we don't have to look at all the metrics. by checking just two columns, the syndromes and the cosset leaders, we can decode it faster. So we name the syndromes by Z, and we name the cosset leaders by F of Z. And what are the decoding steps? So step 1, for a received vector Y, we calculate its syndrome. When we calculate the syndrome, here we locate it in this first column, and then what we decoded by just taking its difference with the FZ here. So for example, we have a received vector Y and its syndrome, it is this one. Then we just go here, and then the received vector will be Y minus this cosset leader, and then we will find the code word. If you calculate the syndrome and of a received vector and you don't find it in this column, then we seek for a retransmission, because it means that the vector has more than 2 errors, and that is no good for us. So this was one of the other decoding, which is faster than the other one. And
Antigona, do we see, could you go? Do we see syndromes as a matrix?
What do you mean?
Matrix, I don't know.
As
2 cross 4.
Yeah, the syndrome itself, it is 1 by n minus k matrix. So in our case here, n was 4 and k was 2. So yeah, 1 by 2, right? Yes. So
okay.
Yes, this is a vector actually. And you said as a matrix, so if we lined it up here, this can just be as a 1 row matrix, or it's a vector, I don't know.
Okay.
Usually they call this the lookup table, so it is just a table with like this too. Sorry. And that's how they look at it. But you can also present it as a matrix with 2 rows.
All right.
Okay. But I have time. I think it's all. Okay.
I have about 2 minutes, 3 minutes, if you like.
Okay, so this is all what I wanted to say. I just will add this. So we're always trying to find the code with the minimum distance. So there is this bound called singleton bound that they always ask the question, so given the distance, can we find a code which is perfect for what they're trying to accomplish, and they give this singleton bound. So for linear codes, if C is a linear code, then I know that the dimension, it is less than or equal to n minus d plus 1, where n is the length and d is the distance. And also if this inequality becomes equality, then those linear codes are called maximum distance separable MDS codes. And I gave an example of such a code. If there is this code called Reed-Solomon, which so it satisfies the equality of this singleton bound, and also it's an error correcting code that was introduced by Reed and Solomon in 1960s, and they use it in a lot of applications. Here I just wrote the consumer technologies applications such as CDs, DVDs, QR codes, and so on. So yeah, that was all I wanted to say.
Thank you very much.
Thank you very much for listening to me.
That's very nice. I'm checking if I have any question. Do you have any question or comments? No, we don't have, I think. Yeah, we may finish here. But let's take a photo of today for memory.
Thank you.
If you want to open your cameras, that would be nice. Okay. Thank Thank you very much.
Sanırım. Evet. Ha, çektin mi? Bir saniye. Ben de çekeyim.